So, welcome to module 24. In this module, we will discuss the expectations of functions of random vectors. To let us see the setup we have. So, suppose x, which is x1, x2, xp, is a p-dimensional random vector, which is either of discrete or absolutely continuous type. And suppose Sx is the support of x. Fx is probability mass function in the case of discrete random vector, or the probability density function in the case of absolutely continuous random vector. And suppose Sxi is the support of marginal distribution of xi, and Fxi is the marginal PMF or PADF of xi. So, we know that one can get the marginal PMF or PDF from the joint PMF or PDF by summing out or integrating out the unwanted variables. So, now let me state the first result. So, let psi be a function from Rp to R. So, if psi is a function from Rp to R, then we know that psi x is a real valued random variable, and suppose I have to find the expected value of this real valued random variable expected value of psi x. A way to do this would be, first you find out the distribution of psi of x, find its PDF or PMF, and then if this random variable is y, so find the PDF or PMF of y, and then you integrate or sum y along with the PDF or PMF. But this theorem gives us a simple way. It says that you do not have to find the PDF of y. What you do is, to get the expected value of psi x, you just sum psi x along with the probability mass function of fxx in the discrete case, and integrate psi x along with the probability density function of fxx in the absolutely continuous case. So, this result is very useful in the sense that by using this result, we can avoid finding the probability density function or probability mass function of random variable y is equal to psi x. So, I can get expected value psi x directly through the PMF or PDF of x. So, let us move to the next slide. Now, let me define a function of two random variables, which is called the covariance between x and y. So, let x and y be two random variables. The quantity which is expected value of x minus expected value of x multiplied by y minus expected value of y. If I take the expected value whole, then this is called the covariance between x and y. So, suppose that so if you, for example, in this case, if you define S to be a random variable x minus expected value of x, t as y minus expected value of y. Note that expected value of x and expected value of y would be constant. So, it is x minus a constant, which is expected value of x, t is y minus expected value of y. Then expected value of St, if you look at, this is nothing but covariance between x and y. So, that is how we define covariance between x and y. Now, covariance x y has the same units as units of x multiplied by units of y. So, to make it independent of unit, I divide it by square root of variance of x and square root of variance of y, and the quantity we obtained, we call that as a correlation between x and y. So, suppose that variance of x is positive, variance of y is positive, then the quantity which is covariance of x y divided by square root of variance of x and variance of y is called the correlation between x and y, provided these expectations exist. So, clearly correlation is independent of units of measurements of x and y. Now, I would say that random variables x and y are uncorrelated if the correlation between x and y is 0, and I will call them as correlated if correlation between x and y is non-zero. So, this defines the covariance between two random variables x and y. Now, let us look at what is the covariance between x and x. Covariance between x and x would be nothing but expected value of x minus expected value of x multiplied by x minus expected value of x, which is nothing but expected value of x minus expected value of x whole square, which we call as variance of x. So, one thing is clear, that if I have to look at the correlation between x and x, which is nothing but covariance between x and x divided by square root of variance of x to variance of x and covariance xx is variance of x, so this becomes 1. Now, we know that we have a simpler formula for variance of x is nothing but expected value of x square minus expected value of x whole square. We try to derive a similar kind of a simplified formula for covariance of x y. So, let us look at what is the covariance of x of y. This is expected value of x minus x value of x multiplied by y minus expected value of y. So, the inside the expectation expression I try to bracket. So, that becomes x phi minus expected value of y into x minus expected value of x into y, and then plus expected value of x into expected value of y. Now, note that here expected value of y is a constant, expected value of x is constant. So, here this whole thing is constant. So, and expectation is linear. So, this would be same as expected value of x y minus expected value of this quantity, but in this quantity expected value of y is constant. So, that goes outside over here and it becomes expected value of x. Similarly, expected value of this quantity when we talk about here, this quantity is constant, which is expected value of x. So, that goes outside and then you get expected value of y, and this whole quantity is anyway constant, and expected value of constant is same as that constant. So, this is same as this. So, this and this gets cancelled. So, you are left with expected value of x y minus expected value of x into expected value of y. So, covariance of x y is nothing but expected value of x y minus expected value of x into expected value of y. So, for example, if one has to talk about variance of x, so covariance of x and x would be expected value of x square minus expected value of x into expected value of x, and that is this formula. One thing is to be noted that covariance x y is symmetric in x and y. For example, if you look at covariance x y over here, this is x minus value of x, y minus value of y. I can write down this as y minus expected value of y into x minus expected value of x. So, that is why covariance of x y is same as covariance of y and x. And due to this, correlation between x and y is also same as covariance between y and x, because correlation between x and y is nothing but covariance between x and y divided by square root of variance of x, variance of y. So, there is a symmetry over here also. So, covariance x y and correlation between x and y are symmetric in x and y. Another thing which one has to note is if x and y are independent, then if I have to look at expected value of x y, let us look at in the absolutely continuous case. This is same as x y, and since x and y are independent, their joint PDF is same as the product of margins. So, this is same as f x x f y y dy, and then you can separate out these integrals x f x x dx multiplied by y f y y dy, which is nothing but expected value of x into expected value of y. So, if x and y are independent, then expected value of x y is same as expected value of x into expected value of y. So, that is why covariance of x y would be 0, and if covariance of x y is 0, that is implies and implied by correlation between x and y is 0. So, clearly if x and y are independent, then covariance is between x and y is 0, also the correlation between x and y is 0. However, the converse may not be true. That means, if covariance is 0 or correlation is 0, that does not imply that x and y are independent. To see this, let us consider this example. So, let x y be an absolutely continuous bivariate random variable vector with joint PDF given by this. One can easily check that this is a proper PDF. I have to show that x and y are uncorrelated, but not independent. So, let us try to see what is expected value of x y. Expected value of x y would be integrate x y with the joint PDF over the whole R2. Now, density is only positive in this range, which is 0 less than mod of y less than or equal to x less than 1. So, that means, and their density is 1. So, that means I have to integrate 1 along with x y over this range. So, if I look at this range, what I try to do is I first fix x as a free variable. There is x over here. So, x as a free variable can go from 0 to 1. Now, for a fixed x, y is such that mod of y is less than or equal to x. So, that means y is between minus x to x. So, for a fixed x, y can go from minus x to x. So, that is good. and this because of this integral minus x to x and y being odd function, this would be 0. So, expected value of x y turns out to be 0. By the same logic, expected value of y would be same as 0 to 1 minus x to x. Now, I have to integrate y along with 1, which is dy by dx. Again here the inner integral, which is y, you have to, which is a odd function, you have to integrate it from minus x to x. So, this would be 0. So, covariance of x and y, which is expected value of x y minus expected value of x into expected value of y, turns out to be 0. So, correlation between x and y turns out to be 0. Now, to check whether they are independent or not, let us make a quick test based on the supports. Clearly, support of x and y, if I look at support of x and y, this is collection of all those x y's such that 0 less than mod of y less than equal x less than 1. Whereas, if I have to look at support of x, what would be support of x? X, the first coordinate can take any value from 0 to 1. So, it would be closed interval 0 to 1. Support of y would be nothing but mod of y less than 1. So, y between minus 1 to 1, and support includes the boundary points. So, S phi would always be between minus 1 to 1. So, clearly you can see that S x y is not equal to S x cross S y. So, just by observations that was also obvious due to the fact that here the ranges of x and y are intermixed. So, this suggests that x and y are not independent. So, here we have a situation where x and y are uncorrelated, but x and y are not independent. So, this is what it says, S x and S y are given by 0 1 and minus 1 and 1 respectively. S x y, the joint support of x and y is this region, which is not equal to S x cross S y. So, this implies that x and y are not independent. Now, let us do the second result, which says that x is a p1 dimensional random vector x 1 x 2 x p1, y is a p2 dimensional random vector y 1 y 2 y p2, and suppose a1 a2 ap1 b1 b2 bp2 are real constants, then provided the involved expectations are finite, expected value of sum of a I x I is same as summation I is equal to 1 to p a I x I, which is straightforward to prove, as we will see. And covariance is also linear, in the sense that covariance of summation I is equal to 1 to p 1 a I x I is same as summation j is equal to p 2 b j y j is same as summation I is equal to 1 to p 1 j is equal to 1 to p 2. You multiply a I with b j, and then the take covariance between x I and y j. So, it is linear in that sense. So, let us try to prove this. Proving this is not difficult. But before that, let me state another result, which is a particular case of part P. Variance of summation I is equal to 1 to p a I x I is same as, first you consider just sum of the variances of a I x I, which is sum I is equal to 1 to p 1 a I square variance of x I. Then you consider covariances between the different a I x I and a j x j, which is same as a I a j covariance x I x j for I not equal to j. You can write down this in a further simplified form, this same as summation I is equal to 1 to p 1 a I square variance of x I. Now, note that covariance x I x j is same as covariance x j x I is same as covariance x j x I, and a I a j is also same as a j a I. So, that means here each term would be occurring twice, one for I less than j and one for j greater than I. So, I can make it 2 times, and I can force this condition on subscripts that I has to be less than j. So, this is 2 times a I a j covariance x I x j. Let us try to see the quick proof. So, expected value of summation I is equal to 1 to p 1 a I x I, that means I have to integrate out this quantity along with the joint PDF of x, and I know that integral of sum is same as sum of integrals. So, it would become summation a I x I f x x, but a I is constant. So, that goes outside the integral and it becomes this. So, here I am integrating out x I with the joint PDF of f x x. So, by a result which we did just now, this is same as expected value of x I. So, that proves the part A, that means expected value of random variables is linear. Expected value of summation a I x I is same as summation of a I expected value of x I. Now, let us look at the next result, which is about covariance of this quantity and covariance of this quantity, right. So, to get the covariance, what I have to do is I have to look at the quantity, its expected value, this quantity minus expected value, and then I have to consider expected value of product of these two. So, first I see what is expected value of summation I is equal to 1 to P1 a I x I minus its expectation, which is same as summation I is equal to 1 to P1 a I x I. By last result, expectation is linear, so this becomes summation I is equal to 1 to P1 a I expected value of x I. So, I combine the two terms, this becomes summation I is equal to 1 to Pi, a I becomes common, and then x I minus expected value of x I. So, that is what you get. Now, similarly, I look at summation j is equal to 1 to P2 Bj Yj minus its expected value. So, that would be nothing but summation j is equal to 1 to P2 Bj times Yj minus expected value of Yj. So, to get the covariance between this and this, I have to consider the expected value of product of these two quantities. So, let us do that. So, covariance of summation I is equal to 1 to P1, j is equal to 1 to P2 is nothing but expected value of the product of the two quantities. So, this is summation I is equal to 1 to P1 a I x I minus expected value of x I, then summation j is equal to 1 to P2 Bj Yj minus expected value of Yj. So, what I have done is I have done a term by term multiplication. Now, expectation being linear, this is same as summation I is equal to 1 to P1, j is equal to 1 to P2 a I Bj, then expected value of this quantity. But expected value of this quantity is equal to covariance of x I and Yj. So, that is what you get. So, that proves part B. To look at part B, which is variance of summation I is equal to 1 to P1 a I x I, variance is same as covariance of random variable with itself. So, covariance of summation I is equal to 1 to P1 a I x I, summation I is equal to 1 to P1 a I x I, which by this result gives me summation I is equal to 1 to P1, j is equal to 1 to P1 a I a j, covariance of x I and x j. Now, I take when j is equal to I. So, this becomes summation I is equal to 1 to P1. When j is equal to I, you get covariance a I square covariance of x I x I. Then you look at I not equal to j, a I a j covariance of x I and x j. That is what will be done now. So, this becomes I is equal to j terms, a I square covariance of x I x I and j, I not equal to j, a I a j covariance x I x j. But covariance of x I and x I is same as variance of x I. So, this is same as variance of x I. So, this becomes summation I is equal to 1 to P1 a I square variance of x I plus I not equal to j, a I a j covariance x I x j. I can simplify it because covariance x I x j is same as covariance of x j x I and a I a j is same as a j I. So, that means each of these terms would be occurring twice when I is less than j and when j is greater than I. So, this becomes 2 times summation I less than j, a I a j covariance x I x j. So, this is what the result of variance of summation. Now, let us do this result. So, let x1, x2, xp be independent random variables, where xi is Ri dimensional. Let psi I is a function from Ri to R, and these are p functions. Then expected value of product of psi I xi is same as product of expected value of psi I xi. So, it says if x1, x2, xp are independent, then expected value of product of functions of these random variables is same as product of expectations of these random variables, expectation of functions of these random variables. Similarly, if AIs are the sets which are subsets of Ri, then probability that xi belongs to AI for I is equal to 1 to p is same as product of the probabilities xi belonging to AI if they are independent. Let us try to prove this. So, let R is summation I is equal to 1 to p Ri, and the vector x is x1, x2, xp. So, x1 is R1 dimensional, xp is Rp dimensional. So, this whole vector x is p dimensional. So, now suppose AIs are subsets of RRIs, that is RI dimensional equivalent space, then probability that xi belonging to AI I is equal to 1 to p would be same as summation I is equal to 1 to p probability xi belonging to AI. So, let us try to prove this result. So, let R is same as summation I is equal to 1 to p Ri, and x is a vector x1, x2, xp. So, note that x1 is R1 dimensional, xp is Rp dimensional. So, as a vector x is R1 plus R2 plus Rp, which is R dimensional. Now, then we have fx of x1, x2, xp as product I is equal to 1 to p fxi xi for xi belonging to Ri. This is due to the fact that x1, x2, xp are independent. So, I look at expected value of product I is equal to 1 to p psi I xi, which is same as integrating summation I is equal to 1 to p psi I xi along with the joint PDF of x1, x2, xp over the whole range RR. Now, but I know that because of independence fx of x1, x2, xp is same as product of this. So, I write down this fxx as product I is equal to 1 to p fxi xi, which, and here you have product I is equal to 1. So, now what is happening is that this whole integral RR has been broken into integral over RR1 up to integral over RRP, because R is same as R1 plus R2 plus Rp. So, now by doing so, now we are in a position to break these integrals. So, I can make it psi 1 x1 fx1 x1, then integral psi 2 x2 fx2 x2, and so on. So, if I do that, so first I write them like this, and then these can be integrated out separately, because these variables have been separated out. So, these integrals can be separated out. So, it becomes product I is equal to 1 to p RRI psi I xi fxxi dx, and this quantity is nothing but expected value of x psi I xi. So, this is what you get. So, this proves the first result, which says that if x1, x2, xp are independent random vectors, then expected value of product of psi I xi would be same as product of psi I xi. Now, the second result follows by just taking psi I xi function to be this, then expected, then I know that product psi I xi is nothing but 1. This would be either 1 or 0, this quantity. This would be 1 if all of them are 1. So, that means if xi belongs to AI for I is equal to 1 to p, and 0 otherwise. And so, expected value of product psi I xi would be same as 1 times probability of this, which is probability that xi belongs to AI. And expected value of psi I xi is nothing but 1 times probability that xi belongs to AI. So, if x1, x2, xp are independent, by the last result, expected value of product psi I xi is same as product of expected value of psi I xi. And this we have seen is nothing but probability xi belongs to AI for I is equal to 1 to p is same as product of these probabilities, and that is what we have to conclude.